Arash Amini from UCLA, and they're going to tell us about matched bipartite block.
Thank you. Thanks, Peter, and thanks for inviting me. Thanks, everyone, for coming. This is joint work with, ongoing work with Zahra Rezai and Jessica Lee at UCLA, and let me just jump into because of the time. Community detection is a popular topic in network analysis, and many people in this room have contributed to this area, and it's has seen a lot of significant advances. I'm going to talk about a particular problem in this area, namely community detection in the bipartite setting. So there are many examples of bipartite networks, and here's a list. I mean, you could come up with a lot more. And the issue is that the community detection in bipartite setting is challenging if you have tried to do it. One of the questions is that how to what do you mean by doing community detection in that setting? The common approach is doing this one mode projection. So you project, so you have two sides. So maybe you have this bipartite network, and I'm going to call each one a side, sometimes a group. So you project onto one side. So for example, you can, if you look at the adjacency matrix, you can form AA transpose or A transpose A, and then do community detection separately on each side. For example, if you do spectral clustering on these two, you would get like an SVD or what they call biclustering type algorithm. And there's advantage in doing that. There's a moderate reduction in dimension, especially if one side is very small. But there's also some disadvantages, mainly that you lose information. So there's an identifiability issue. So you could have two different bipartite networks have the same one-mode projections. And you're also not using the bipartiteness of the network. And the other one is some sort of association between the communities of two sides. And if you care about that, maybe you don't care about that, that's fine. But if you try to do a matching, you have to do an ad hoc sort of matching afterwards. It's not clear how to do it. And I mean, you could argue that having a matched set of communities helps interpretation. So in fact, we're motivated by an example that Zahra and Jessica had. We had an example from biology. So these two are species. So species 1, species 2, and the nodes are genes here. And there is a relation called ortholog. So apparently they were the same gene in an ancestor, and they split. So somehow you want to say that these genes correspond to these genes in the other species. So you somehow like to have a one-to-one matching or mapping between the clusters that you find in each side. So motivated by this, and you also have rich covariate information. So for each gene you have gene expression and over the different time courses because they have different life cycles. So in let's say, in principle, you could have covariates, node covariates that live in different spaces. So you want to also model that. So you try to have a model that has these matched communities built into it and respects this bipartite nature and uses it and allows for these node covariates. So it's a recipe that has many ingredients. But before going into that, let me just review. Fortunately, Sharon talked a bit about block models, and I guess more people are going to talk about it today. But the original block model has this. I'm going to set up some notation. I'm going to vary that. But let me just quickly go through it. So let's say we have n nodes, k communities. And we look at the adjacency matrix, which is a binary symmetric matrix. It's a representation of an undirected graph. There are two other ingredients in this setup. One is this connectivity matrix, which gives you the probability of connection between communities. And a node label. For each node, we have a label, 1 through k. And for example, if you have 5 communities and the node is in the fourth community, you could represent it as a binary vector. You usually identify it with a binary vector of size k, and you sort of concatenate them, these k vectors, you get a matrix. This encodes the latent community structure. Looks like something like that. And then the way that you build the model or the network is that given the latent community structure, you draw these edges. So if, like this, so if I is in community K and J is in community L, you go and put an edge with probability psi K L. And you can write this compactly as a model for the mean of the adjacency matrix using this Z. So you get Z psi Z transpose. So this is rather a nice way to represent this model. Now let's go to the bipartite setting. So you have this bipartite network. You have these two groups or sides, and we label them like this: 1 true and 1, 1 true and 2. And you have a bunch of communities here. Let's say 3 on this side, 3 on the other side. I have the same number because I want to match them. So we're going to assume that there is a priori matching. So now we have the same colors here. So same color means the same matching. But signifies the matching. So you have partitions for each side. So the side is indexed by R. So I have the same number of communities on each side, and they're matched in this way. So C1K is in 1-to-1 correspondence with C2K, K from 1 to K, and then I could assign a group or community membership to node I in group R. I can record that as the Ri, being K if I belongs to the Kth cluster in the R side or I group. And then I also have a covariate associated with these, each node in each group. And so the dimension could be different on the two sides. So D1 on this side, D2 on the other side. Or they could, in general, live in different spaces.
All right.
Yeah.
Same number of communities for two sides.
Right, because I want to have a 1-to-1 matching. That's right.
It could be 1 to 2, right?
It could be 1 to. That's what we wanted to avoid. Yes, that's the. So because at the end, this is. But if you do bi-clustering, that would be a good thing. If you don't want to have a matching. But in the end, they wanted to. So from the biological perspective, you want a 1-to-1 matching. So then you have to run a matching on it. So what we said, why don't we have? It turns out that if you run it on practical algorithms, some of these would be 0. So you could have a community of size 0. This wouldn't be matched to a 0 community there. That would allow that if you allow 0 size communities. Okay. But this is a sort of, let's say, motivated by practical applications. And it also helps interpretability. If you reduce to another graph on communities, then you have to do it. If you have a lot of communities, then you'd end up simplifying it to another graph. Then you have to worry about what this sort of graph means. Well, okay. It's a valid question. But let's say you're interested in this setup. So let me just say a few words about modeling covariates. So this works in general. So it's a general idea even in the regular block model. So we have, let's say, 3 pieces: adjacency, community, and this covariate matrix. This is the simple general idea, is to just model like this. Given Z, model A and X independently. This is the graphical model for it. And then model X given Z as a mixture model. So you go and pick the covariates based on the membership that is determined here. So node I has a membership vector, and you pick from that component of the mixture and generate the X. So if you believe, like me, that the block model is a pi-dimensional mixture model of sort, then this is not that surprising way of modeling things. And in the bipartite setting, we're going to add another variable here, V. You could also add it in the usual case for the reasons I'm going to explain. It will help actually further also reduce the dimension of the model. So why we do that? First, this is a more detailed way of how we build this model. So let's say I have the covariates. Let's say I draw these pairs of covariates. Concatenate them. So it's going to be a D1 by D2 vector. So this piece is in R to the D1. This one is in R to the D2. And I draw from a multivariate normal IID samples, K IID samples. And depending on which side of the network I am, I'm going to take that corresponding piece and generate the covariance. So if I'm, let's say, I'm looking at the node in community K prime, on this side, I'm going to take this piece and generate from it. And if I'm on this side, I'm going to take this other piece and generate from it. And one reason for doing that, we wanted to somehow have some, the covariates have some, we wanted the covariates to carry some information about the matching. And if you have a covariance matrix, if you partition it, and if you have a non-zero diagonal there, then there is some information. I'm going to show a slide trying to argue that. But there is a weak information. In the other motivation, so first, it's hard to do this because these could also live on different spaces. It's not clear how to match things on different spaces. But let's say they're in real value but on different dimensions. The other motivation is that these hierarchical Bayesian models, so this is an idea from a hierarchical Bayesian perspective, they do this quite often, and it helps reduce the number of parameters. So instead of having k times d1 plus d2, you just have a d1 plus d2 times d1 plus d2 covariance matrix. So there is an intrinsic sort of low dimensionality built into it, which is good. So the reason why I believe, for example, that this has some information about the matching is that if, for example, you have zero, let's say, measurement error here, the problem boils down to telling, let's say, v1k, v2k pair from the case where v1k, the second piece is replaced with some other v2k from some other component. And if you write down the joint distribution, it's going to be normal with this type of covariance matrix because we have drawn these IID. So if you look at this piece, it's going to be, let's say, full covariance. Let's say Z1, sigma 1, 2 is not 0. And if you look at this piece, it's going to be 0. So there's information in the model to tell the two apart. But it's a very weak information because you have to distinguish between these two normal distributions based on just one sample for each node. And it's really hard to sort of try to tease out that case where this information is the driving force. It doesn't seem, it's not clear whether this is going to be having any effect. But the low dimensionality is still there. So let me just introduce some notations to write down the model a bit more in detail. So you have, I'm going to put the star here when I collect over R, star here when I collect over K. And
can we just make that much easier for you?
Really?
Yeah.
It's not going to, okay.
Yeah.
And then you collect everything so I collect everything into these capital, so V, Z, and X, collect the covariates, the memberships, and the V's. And this is the part that I explained. So you to generate the covariates, you take the Z's over the sides and over the node in each side independently from multivariate normal. And then and you generate from these V's both components from a multivariate normal. And then depending on which side of the network you are and which community you are, you go take the correct piece and then generate from that. It's a fairly simple hierarchical model. And now let me tell you, and you can also replace these Gaussians later on with binary covariates and stuff like that. The good thing about mixtures is that they're flexible. So if you have binary and other type of covariates, you write down the likelihood and they're combined naturally with each other, so you don't have to worry how to combine them. How to generate A, there's something there too. So the way we generate this is, let's say I and J are on different sides. I will put an edge between them if they're in a matched community with some probability P and otherwise some probability Q. And then you can generalize this to a general stochastic block model if you have a general connectivity here. But we're going to focus on this. So let me tell you how this is related to a usual block model. You can think of this as an SVM on N1 plus N2 and 2AK communities, but with some restrictions on both the membership and connectivity. So the connectivity is clear because of the bipartiteness, but it also imposes some restriction on the membership because of the matchedness of the communities. So if you write down the symmetric adjacency matrix like this, and then you have these Z1 and Z2 are the labels of each side, and then you just form this block diagonal case Z tilde, and this is going to be psi tilde. Then you can see that you can write that this is going to be a model for this. I mean, this is the model for a expected adjacency matrix, and it looks like a block model, except that there is some restriction. I mean, these can't be any. These two k's are restricted somehow, that this side should be 0, this side should be 0. That's the matching. And the connectivity should be 0 on the diagonal, which means that it's bipartite. And whenever you have this restriction, then there's a natural matching in the sense that the community k and community k plus 1 are matched, and so on. Okay. And then there's some question of how to do cluster quality evaluation, because I told you about this Z tilde. There are a couple of things that you could do. Usually you do normalized mutual information between labels, and you could compute the NMI, normal mutual information between ZR and the estimate of ZR individually. That gives you some measure. You could do it between these Z tildes, which we haven't taught what that means, or you could do it like this. So Z, you stack them up together, Z1 on top of Z2, and you do NMI between these, and this we'll call matched NMI, because thinks of the matched community as one giant community, and does it measures how well you did the matching too. So I'm going to just skip over this quickly. So you can write down so the way that we fit it is just by doing this mean field variational approximation to the likelihood, because the model is a bit complicated. So you can write down, so there's this Yij, which says whether I and j are matched. And you write down the pieces of the likelihood. This piece that depends, for x is fairly general. You could have other likelihoods there, and you have this factorization for the joint distribution, the a given z and then x given zv, and then these two are independent. You write down the joint, and then this is the log likelihood if you have all the latent variables. And there's it looks a bit lengthy, but this is the part from the block model. This is the part from the, I mean, it contains both, so the mixture and, so you have the labels, and they interact via this, the labels and the covariates and this hidden layer, and then this hidden piece here. And the way we do it is by this is, whenever you have a very complicated likelihood with many latent variables, one way that people deal with this is to subtract this log term. I mean, this QZ of, you don't observe Z and V, so this is a surrogate posterior, or proximate posterior. Subtract this and then take the expectation with respect to Q. That would be like an entropy term. And this would be a lower bound of the likelihood. And if you put the true posterior here, that would be EM, but we do an approximate posterior and then try to optimize both over Q and the parameters of likelihood. We do the mean field approximation. I mean, everything is a product, so this factorizes into two pieces. On Z, we have also factorized over each label. We could do maybe better approximations here, but we do the mean field, and then this is a general multinomial for each one of the labels. So you have these key parameters, tau Ri. These are the posteriors on the labels. And these are the things that we're interested at to recover. Each one is a probability distribution under the communities for the node indexed by R and I. And then we have to specify something for V, and we do specify a mixture of Gaussians. And this form is actually suggested by the posterior. If you look at the posterior, V given Z, it has a mixture of Gaussians form, but these means and the covariances are horrible expressions in terms of Z and A, so we just ignore the expressions. I mean, we assume that there is some mu tilde and sigma tilde. So if you plug that in, I mean, after the dust settles, you get this expression for the variational distribution, which is actually simple to optimize if you do it coordinate-wise. There's some piece, the Gaussian likelihood appears here, the likelihood that the Bernoulli appears there. There's some key parameters. There's this data that is the effect of the covariates on the labels, as you'll see. This is how the covariates affect the labels. And this piece is, in the end, is going to be the estimate of the sigma. It's like a sample mean for the, based on the hidden sort of means. So let me just, for example, show you the updates for tau, which are the interesting ones. So we do, for example, block ascent. So you have these likelihood parameters, and so this gamma collects the parameters of the surrogate posterior, or the variational sort of posterior, if you want. Then, and then you block coordinates sort of update everything. And for tau, it looks, the updates are rather simple. There's this piece that's coming from the Bernoulli likelihood, and this is the contribution by the covariates. And there's some interpretation of this. I don't know if I want to talk about it. Let me quickly mention that this is just the likelihood of Bernoulli, and if you believe that your graph is sparse, P and Q are very small, then you can approximate this with alpha times log P over Q. Then this simplifies greatly. Let's forget about these covariates for now. It would look like something like this. So you pass this tau 1, tau 2, stack them together through this A tilde, and then you normalize by your row-wise softmax operation. So it has the feel of a power iteration, but a different normalization. And it would be interesting to analyze something like this, I think. This is a bit more complicated. It has these non-edge effects, which might actually be helpful. But even this simple case shows some interesting sort of features and simulations. And these are the updates for the other parameters. They're rather simple, more or less standard. There's some matrix inversion involved, but nothing fancy. Okay, so I'm just going to, okay. So I'm going to just show you some simulations and wrap up. The simulation setup, let's fix the sizes like this. There are these key parameters in covariate generation, which is mu is not important, so just say mu equals 0. And then I'm going to just take the simplest sigma, which is mu times identity. And if mu is 0, then there's no covariate information. As you increase, you'd expect there's covariate information increases. And there are key parameters in the network generation are P and Q. So usually the people normalize by some form of degree that determines the hardness of the problem. So we normalize by the expected overall degree, which we call lambda, and then this out-in ratio alpha we usually set to be fixed. So the smaller the lambda, the sparser the network, the more difficult the problem. And the community sizes are roughly equal for this simulation. And a few words about initialization. So you initialize by perturbation of the true labels. This sort of simulates the case where we have you have a good initialization, and then you could also initialize by the spectral clustering and the perturbation of clustering with perturbation. When you skip over this, this is a typical situation that you get. For example, if we have no covariates, this is our method, sort of, which is started with a perturbation of the truth, and this is the spectral clustering with perturbation, and this is the pseudo likelihood that we have with Peter and Lisa and IU, and this is the other one started with our method started with SCP. And if you add covariates, this is what happens. So you expect that quiet information helps when the graph is very sparse, and indeed it does that. So these are shifted downward. Skip over that. The effect of covariates I mentioned is good. So as you have more covariates, these would get better. The last thing maybe I want to talk about is some interesting thing happens when you run it on some real networks. We don't have networks with ground truth labels. We just try to run it on something and see what happens. Here's an example of a network, bipartite network. And I just quickly want to show you what happens if you fit with k equals 3 and just random initialization. This is the spectral clustering. This is starting R method with spectral clustering. And if you run it with k equal 5, k equal 10, k equal 20, k equal 40, then you still see that there seems to be a giant, I mean, there is one matched cluster, and maybe the rest are noise. This recovers something which I'm not quite sure whether there is there. But the interesting thing is that it doesn't seem to be sensitive to the number of clusters if you initialize it randomly. So you could throw in a large number of clusters, and if it has it seems that it has a sort of regularization effect on the number of clusters. So you end up with all of them being essentially 0 except V1. And a similar thing we observed in another, for example, Wikipedia example. This is the random case. And you can see these are the distribution of the labels among clusters. So for example, if you look at how you assign labels to clusters, most of them are 0. You just recovered about 4 clusters in these cases, whereas the spectral clustering with 40 clusters or 20 clusters, they just have a lot of unnecessary clusters. Okay, this quick conclusion is that we have a simple model which allows for match clustering. We have, let's say, a fast likelihood-based fitting approach. There are some promising performance in simulations, real data, and there is some tendency, it seems, to regularize the number of clusters. We don't know why. This is the wish list. We would like to have some theory. I'm not sure what kind of theory is useful in this setting, but maybe some degree correction, better modeling of correlation among matched clusters, which is not, in general, easy to do. Conceptually, it's not clear how to do it. How we tune the covariate information versus the graph information, comparison with some convex relaxation we can also do in the covariates, and I guess Purna is going to talk about this on a Friday. And also this restriction of the membership has idea I think is useful if you want to model multi-layer multiplex. This is like a multi-layer network. If you remove the restriction on the connectivity, but keep the restriction on the membership, you could sort of try to visualize or envision multi-layer community detection using this type of approach. Thanks.
Well, it's
Yeah.
run over, but then we can just run a little bit into the later. So, some questions? Well, if not, I guess.
Okay.
Thanks. All right.